You have seen free body diagrams already. I just haven't sort of come right out and said. I've kind of alluded to the fact that kind of said, yeah, we're going to talk about those later. Today's the day. Okay? And these come in handy when you're solving just about any physics problem from here to the end of your physics career. Okay? So it's sort of a big deal in some senses. And you've probably already seen them in grade 10 already, but this is probably the first time that you've actually formally talked about them. So, free body diagrams are diagrams used to show the relative magnitude and direction of all forces acting upon an object in a given situation. When I say relative magnitude, what does that mean? Well, magnitude means the size, and relative magnitude doesn't mean that they're related to each other, you know, like family, brothers and sisters, not that kind of relative, right? Relative magnitude means that bigger sizes have bigger arrows. That's what it means. A free body diagram is a special example of vector diagrams. These diagrams will be used throughout the study of physics, as I said. The size of the arrow in a free body diagram is reflective of the magnitude of the force. In other words, bigger forces, bigger arrows. The direction of the arrow reveals the direction in which the force acts. Each force arrow in the diagram is labeled. Why did you think I emphasized that? Each force arrow in the diagram is labeled because there's always some individuals who refuse to label them because it takes so much time. You guys don't have this, right? Oh, it's on the very back page? I very much apologize. Apparently I have them in the wrong order when I copied them. You know what? I think I have them in the wrong order on the slide. But we'll go through this. It's okay. We'll do it this way. Yeah. Okay. It's okay. I'll just do it in a different order this year. No big deal. Okay. So as I said, we want them labeled. Okay? It's customary in a free body diagram to represent the object by a box. Some textbooks just use a little dot like this. In other words, if it's a bicycle or a car or a rocket ship or a semi or whatever, it doesn't matter. You can just draw a little box because your artistic abilities doesn't matter. Some people still insist on doing that because they are artistic. That's fine. But technically, it's not supposed to be more than a box. And the force arrows from the center of the box outward in the direction in which the force is acting. Okay? So even if it's a push, we show it as a pull. It's just a convention. Okay? Even if it's pushing from the left to the right, you show it as a pull to the right. So we can't tell if this applied force is a pull or a push, is what I'm saying. One example of a free body diagram is shown about right here. What would you say about those forces, relative speaking? Are they about equal? Are they balanced? Yes. Did we get on a ruler? No. No. Okay. If they're supposed to be balanced, they should look like that. Balanced. Am I going to get on a ruler and figure out if it's half a millimeter longer than the other one? No, I don't have time for that. But if one of your supposedly balanced arrows is about 1.5 centimeters longer, you're going to have a problem. Okay? So please try to make them eyeballish equal. The free body diagram above depicts 4 forces acting upon the object. Objects do not always have 4 forces acting on them. There could be many more. Could be less. Problem there, Andrew? No? Okay. There will be cases in which the number of forces depicted by a free body diagram will be 1, 2, or 3. There is no hard and fast rule about the number of forces which must be drawn. The only rule for drawing free body diagrams is to depict all the forces which exist for that object in a given situation. You have to draw all the forces. Thus, to construct free body diagrams, it's extremely important to know the types of forces. We did those back on day 1 or day 2, right? Buoyant force, friction force, tension force, blah, blah, blah. Okay? All of the forces usually are labeled with an F, and then there's a subscript that is a label for that type of force. F norm, normal force. F grav, gravitational force. F ap, applied force. F friction force. I don't use those particular ones. You can use your own if you want. Okay? It doesn't matter. That's just a sort of a labeling procedure. It's like putting, your name on your, binder.
If given a description of a physical situation, begin by using your understanding of the force types to identify which forces are present. Then determine the direction in which each force is acting. Finally, draw a box, add arrows for each existing force in the appropriate direction. Label each force arrow according to its type. Okay, so that's sort of an introduction. And then, you know, we're going to come back to those. This should be last. So just pause for a second. Go back. Okay. So this is the lesson on free body diagrams, another version. That's all. Okay? And this one's sort of more detailed. We're going to go through it, and then we're going to do those practice ones on that last page. I apologize for messing that up. So free body diagrams, otherwise known as FBDs, that's another way to describe them, are simplified representations of a problem of an object, the body, and the force vectors acting on it. This body is free, air quotes, because the diagram will show it without its surroundings. Right? It eliminates unnecessary information which might be given in a problem. Let's take this figure to be a pictorial representation of a situation. A sled on snow with horses pulling it. First we'll represent the sled. The body in our diagram is a really simplified figure, a square resting on a flat surface. So just a box, right? Okay, so we're going to do the first one here. The first force we'll investigate is that due to gravity, and we'll call it the gravitational force. We know that acceleration due to gravity, if it's on Earth, is approximately 9.8. The force by Newton's second law is Fg equals mg. Now, I prefer to call it, there it is there, I prefer to call it Fw, the weight force. That's what I call it. Some books will call it Fg, gravitational force. Some books will call it Fmg. Okay, there's a variety of different ways, but it means the force of gravity, down. Everybody know where you are on the sheet? Anybody lost? No? Good? Note that the force vector labeled Fg or Fw points downward, as this is the direction which gravitational force. Note that this force is also commonly called weight. This weight is different from our everyday use of the word weight, which is known in physics as mass. When someone says, how much do you weigh? And you answer in kilograms, you're really giving your mass, how much stuff you are. Right? Weight is actually in newtons, and I actually have, back there, some of you may have seen it, I have a bathroom scale that's measured in newtons. Only nerds have those in their bathrooms. Okay, normal force. Now, normal does not mean the normal definition of normal. Okay? Normal means perpendicular. Normal force is one that prevents objects from falling into whatever it is they're sitting upon. We've talked about this, equal and opposite, right? Action, reaction. It's always perpendicular. Always perpendicular to the surface with which an object is in contact. For example, if there's a crate on the floor, then we say that the crate experiences a normal force exerted by the floor, and because of this force, the crate does not fall into the floor. The normal force on the crate points upward perpendicular to the floor. It's called the normal force because normal and perpendicular mean the same thing. Okay, I'll find it then. What happens on a ramp like that one? The normal force is always perpendicular to the surface with which a body is in contact. For a body on a sloping surface, say a ramp, the normal force acting on that body is still perpendicular to the slope. Okay, so there's the slope. So this is Fn, perpendicular. Like so. What direction is gravity? Straight down, Fw. Here's a little preview of grade 12. Are those forces balanced? Not entirely. Isn't it just like balanced or not balanced? Is there kind of a in-between? It's either balanced or not balanced, right? So these are not balanced, which means there must be a. Therefore, there is a net force, which means there is a acceleration, which is why things do what? Slide down ramps. Okay, Josh, you can put the phone away. Here's the listening part. So let's add the normal force to our FBD and represent the normal force with the letter Fn. You should have it there, do you? Or do you have to draw it in? I can't remember. It's there? Okay. There are some textbooks that will show it, and you might see it online. Some books show it like this. Do you know what that sign means? Upside down T. Perpendicular. Friction. Friction is related to the normal force. Related to the normal force is friction. The two are related because they are both due to the fact that the body is in contact with the surface. Whereas the normal force was perpendicular, friction is always parallel. Furthermore, friction opposes motion. And so its vector always points away from the direction of movement. Friction is divided into two types, static and kinetic, and we'll get into that a little bit more later. These are represented by FF, force, friction. I call it friction force, but that's really what the F, big F, small f stands for, right? With a further subscript F or S for static and the subscript K for kinetic friction. I don't normally worry about that. You might see it in some books. As its name suggests, static friction occurs when the body is not moving with respect to the surface. Static means not moving, not changing. It's the force that makes it difficult to start something moving. On the other hand, kinetic friction occurs when the body is sliding over the surface. Rolling objects experience friction as well. That's for another day. This is the force that causes objects to slow down and eventually stop. Friction is usually approximated as being proportional to the normal force. The proportionality constant is called the coefficient of static or kinetic friction. And we will get into this a little bit more later, but that's something that you will end up knowing. The coefficient of friction. The coefficient is represented by this funny looking symbol right there. Can you make it out on yours, on your page? Does anyone know what that symbol is? It's the Greek letter mu. Mu. It's the Greek version of M. We interpret it as a U with a tail on the front. Okay, so you sort of put that big swoopy tail on the front, and then you make yourself a U, and it's pronounced mu. Mu. Mu S for static friction, mu K for kinetic friction. The numerical value of mu depends upon the nature of the surface with which the body is in contact. So things that are really rough, well, there's lots of grip, like say rubber tires on asphalt, dry asphalt, pretty grippy, right? The mu value is going to be high. Teflon sliders on curling ice, really low mu value, not a lot of friction. Okay, pushes and pulls and other things. Another force which may act on an object could be in physical push or pull. This could be caused by a person pushing a crate on the floor, a child pulling on a wagon, or in the case of our example, a horse pulling on the carriage. We're going to label the applied push or pull with FA. This is what I call it, applied force, FA. Applied force, right? Could there be more than one applied force? Sure. What would you label them if there's more than one? FA1, says Renee, FA2, and so on. Sometimes I'll just go F1, F2, right? Whatever. The labeling really doesn't matter a whole lot. Right? You can come up with your own kind of system. Tension. Are you worried about this part? Little joke there. Worried about tension? Okay, never mind. This wasn't funny? Oh, okay. Tension in an object results if the pulling force acts on its ends as it's in a rope. If we say our carriage is being pulled by a bar at its front end, then we can add this force to our FBD. So sometimes the applied force is a tension. I tend not to label things with T for tension. Just applied force. There we have it. All the forces acting on a carriage have been labeled in the figure. This is the complete FBD for a problem of a carriage being pulled along a road. Is this object moving? Yes. Have I not asked that question many times before? Must it be? Think, all right, for a second here. Does that object have to be moving? Yes. How come? Because there's a net force. The forces are not balanced, right? There is a net force to the right, which means there's an acceleration. So if it was at rest before, it's going to start moving. And if it was already moving, it's either going to be slowing down or speeding up. So yeah, this one's moving. Okay, here's a couple of examples. Child next door wants to take his German Shepherd named Spot for a ride on a sled. I didn't write this. Don't. Yeah. He chases Spot, who's running away while dragging the sled behind him. What forces are acting on the sled? Okay, so we discussed gravity, normal, friction, push or pull. What forces are acting? Well, since the question does not state otherwise, we'll assume it's all happening on Earth. That's a pretty general assumption. Once it says otherwise, you can assume Earth. So gravity is acting, gravitational force is pulling down. Do you have the box over here on the right? You do. Do you have the forces? You do not. Okay, so weight force. I tend to draw mine starting in the center of the box. Other conventions have it like this. Okay, doesn't make a whole lot of difference. The sled is being dragged on the ground, which we can take to be another surface. This surface exerts a force on the sled, preventing it from falling into the ground. Thus, there is a normal force on the sled. It is up. Are those two things balanced? They should be, right? It's a kid pulling a sled on the ground. It's not accelerating up or down. Those should be balanced. Are those close enough without pulling on a ruler? I would say so. Because the sled is in motion and the surface with which it has contact is not frictionless, then there is kinetic friction. Now, which way do we draw friction? Did it say which way the sled is pulling? No. By convention, we tend to live in a left to right world because we read that way. So virtually 99% of the time, the friction force is like this, unless it specifically says it's moving to the left. Okay, so usually I put the friction force to the left, but it doesn't have to. Does it say how big it is? We have no idea relative to these ones, but it really doesn't matter because they're not sort of related. The child is pulling on the sled, so there is a pull force, F pull. The pull may not be parallel to the ground, but at an angle as shown. So it doesn't necessarily have to be, it could be like this. Did it say anything about a constant speed? Doesn't, right? So we don't know. It could be like this, or I'm going to do it in a different color. It could be like that, right? And when you get it at an angle, that causes some complications, which we'll get to. Don't worry about it for now. We're just drawing the pictures. All good so far? Okay. Another example. Spot the German Shepherd being walked by his best pal Dot, the Siamese cat. I don't know who makes this up. Actually, Dot is pulling Spot across the ice rink, disturbing the neighborhood hockey game. What are the forces acting on Spot? Well, again, we are on Earth. Gravity. He's on an ice rink, on a surface, normal force. Is there always going to be a normal force? Do you have to be in outer space? Like just that kind of thing? Like, yeah, okay. It's not sitting on anything, right? Gravity's pulling, but it's not sitting on anything. Good. Okay. Now, the cat is pulling the dog across the rink, so we got an applied force. Now, secret code. Ice rink is code for no frictionless. It causes, I will try to be more blunt and say it's a frictionless surface, right? But there are times, textbooks or whatever, online maybe, okay, you will see that ice rink, curling, anything that's kind of icy, they're implying that it's frictionless. So we assume that ice is frictionless, so neither static nor kinetic friction. So it would be like that. And what would that object be doing? Would it be moving, Brady? Yeah, how come? Because there's a net force, right? The forces are not balanced. The push-pull force may be misleading. While it's true that Spot is being pulled along by Dot, this is not the force acting on Spot. This is because Dot is actually pulling on the rope. The rope in turn provides the tension. That's kind of splitting hairs there, I think. Right? They're saying that the cat is pulling on the rope and the rope is pulling on the dog. Not really that important just now. Okay, we got two more examples, I think, right? King Kong. When climbing the Empire State Building, King Kong peeks into one of the corporate windows and sees a poster with Tarzan swinging from a vine. Our furry friend decides he'd much rather be swinging from vines instead of hanging outside of skyscrapers. When King Kong is swinging from a vine, what forces are acting on him? Well, again, on Earth, but he's not on a table, he's not on the ground, he's swinging from a vine.
Normal force? No. No normal force.
Any friction? If he's not on a surface, no friction. Well, how come he's not falling then? Because he's hanging on this vine. So there must be a tension force. We'll label it FT for now. It could be applied force or whatever. But the rope is holding him up, right? It kind of, we don't know enough in the situation. Like it didn't give us any angles, so let's say swinging, right? If it was like this, Dan, if that was true, then would there be a net force? And then the gorilla would be swinging, right? That's why he moves. How come when he's at the right at the bottom, if the gorilla's swinging back and forth like this, like a pendulum, right at the bottom, the tension force is straight up. So how come he keeps moving? And objects in motion, in motion. Okay, the elevator. How about you try this one? You try the elevator. I'm going to go do attendance. You try the elevator, and then we're going to give you the answer. Our furry friend King Kong has had enough of monkeying around and has returned to the Big Apple. Once again, he's up to his tricks with the Empire State Building. Only this time he's taking the elevator instead. While he's riding up to the top of the building at a constant speed. Is that important? How come? Because at a constant speed means that the acceleration is 0, which means that the net force is 0, which means that they are balanced. And it usually makes for an easier word problem. Tyler, put the phone down, listen to me now. Okay. Gravity. Anything else? Normal force up. Balanced or not? Balanced. Anything else? Which way is the applied force? Up. How long should I make it? Like so? Any friction? Which way? Down? You'll notice that I haven't said it's right or wrong. I hear all these people going, "What's wrong?" Okay. Gravity for sure, right? Normal force on a surface? Yeah. Okay. Objects in motion stay in motion. Why do I say that now? Objects in motion stay in motion. So when you tell me, and I'm not picking on people, but when you tell me to add this in, that tells me that you think that you need a force to keep an object moving. I'm afraid not. That's it. The monkey, the gorilla, is already moving, so do you need an unbalanced force? No. Do elevators lift people and monkeys? Well, maybe not monkeys. Do elevators lift objects up? Well, sure they do. But once you get it going, all you need is enough to balance the weight force. When you're standing in an elevator, how does it feel right at the start, when it starts to move? How does it feel? You kind of do this, right? How come? Because there's a greater force, because you're at rest. You're not moving, and then it has to make you moving. So there is an applied force. But once it gets you going, then it's all fine and dandy, isn't it? You just stand there. Right? So I'm afraid that is the answer. Now there is a little bit of friction, right? Because there's wheels and there's like it's sliding on the edge, right? But that is technically on the elevator car, not on you.
There's friction on him though too, static friction.
No, because he's not trying to move, so there is no static friction. Remember the other day when I said, how come the desk doesn't go sliding this way, right? There's only friction when you try to move it. So he's not being tried to move left or right, right? Yeah. It's tricky stuff, I get it. Is there one more example? No, that's it, right? Yeah, okay. So that's where we're going to go back to now. So now what I want you to do, these are the practice ones. There are 11, is that right? Or 9? Some 11, okay. So there are 11 practice questions. I'll give you like 11 minutes, roughly, and then we'll go from there. Okay, some will be hard, some will be easy. Good luck. A book is resting on a tabletop, diagram the force acting on the book. This one's pretty straightforward. Weight force? Normal force, right? Some of you may have drawn this. Did you draw that? Okay. Some of you may have drawn that. I'm not going to get too excited about that. There are some people that say that's a no-no. Because it's a free body diagram, which means you don't draw anything but the thing that the forces are acting on. I'm okay with it. Okay? But I'm just warning you ahead of time. That may cause you some grief in the future. Please do not go and say, Mr. Bennett let us do that. Yeah, I do, because I'm more concerned with process and stuff like that, right? Not worrying about the details, but I'm just telling you. A girl is suspended motionless from a bar which hangs from the ceiling from 2 ropes. Diagram the force acting on the girl. On Earth? Yes. How many people drew a little stick figure girl? Nobody? Okay. Weight force? Now, the fact that there's 2 ropes, does that cause any difference? Yes. Technically, you should have this. And technically, it's a tension. And those 2 arrows should equal together. Oh, I knew I should have done it in a different color. Those 2 arrows should equal, like together, the same as this one. Technically. Okay? Like the total forces down should be the total forces up. I'm not going to get too excited there. Again, you use this as an aid to solve problems, which we're going to get to. Okay? So I'm not going to get all excited about whether you're 1 millimeter too long or that kind of thing. In fact, I would probably, if I'm doing the problem myself, I would just do that and call it applied force up. Right? But there are questions in grade 12 where we've got signs hanging from 2 wires, right? And they're at an angle like that, and we've got components like that. And then if this is 100 down, then I got 50 there, and I got 50 there. So maybe we should have 2. Maybe I should insist on that. That's the reason. An egg is free falling from a nest in a tree. Neglect air resistance. Don't include air resistance. Diagram the forces acting on the egg as it falls. Here's our rather square-looking egg. It's happening on Earth. Anything else, Braden, that we should add? This is number 3, Braden. That's it? Really? You're right. How come? What else is there? It says to neglect air resistance. It's just gravity. Flying squirrel, probably named Rocky. Go ahead.
Air resistance, 3 times the friction.
Yeah, I just call it friction force, yeah. Flying squirrel is gliding, no wing flaps from a tree to the ground at constant velocity. Consider air resistance, diagram the force acting on the squirrel. Right? Gravity, weight force. He's just gliding. He's moving, like, is he doing this? Likely, it doesn't say that. Do I need an arrow going this way? I'm going this way. Do I need an arrow going this way? No! Is there a force going on and going sideways? No! Objects in motion. See, I told you it was going to keep coming back. I'm going to call it FF. Some of you might have, oh, that should be a small f. Some of you might have called it F air. I see that quite a bit. I'm okay with that. Right? Because it's air resistance. I get that. Some people want to do this. Right? Because they know that he's falling and the air resistance is also down. I'm okay with that in this case. Okay, because he's actually going to be slowing down. There's going to be a net force that's going to be slowing down. Okay, so you guys go ahead and try the rest. Understanding. Okay, so number 5, a rightward force applied to a book in order to move it across the desk with a rightward acceleration. Consider friction. Neglect air resistance. Got a weight force. It's on a desk. We got a normal force. They're balanced. There is a rightward acceleration. A rightward force is applied. Why did I draw it so big? Because it needs to be bigger than friction. It's accelerating. Did you have something like that? Good. A rightward force applied to a book in order to move it across the desk at a constant velocity. Consider friction forces. Neglect air resistance. Diagram the forces acting on the book. Weight force. Normal force. Rightward force. There is friction. They are the same. Constant velocity. How come I need... Mr. Bennett, you told me before, even though the thing is moving to the right, I don't need to draw that applied force. How come I have to draw that applied force here? There's friction. The net force has to be 0. When there's no friction, you don't need it. But there is friction here, so it has to be there and it's balanced. Does that make sense, Alex? Yeah? Good. Number 7, a college student rests a backpack upon his shoulder. The pack is suspended motionless by one strap from one shoulder. Diagram the vertical forces acting on the backpack. Only the vertical. Okay, well, it's on Earth. Weight force. Probably FT is technically correct. I'll accept FA, applied. That's it. It's motionless. It's just hanging there. They are balanced. Skydiver is descending with a constant velocity. Consider air resistance. You'd have to, because there's no way he would descend at a constant velocity without air resistance. So we got gravity down and we got friction or air resistance up. They're balanced. Net force is 0. Starting to make some sense? A force applied to the right to drag a sled across loosely packed snow. Code. Rightward acceleration. Weight force, it's on the ground. Normal force, there's a force to the right. Loosely packed snow is code for there's some friction, but there is an acceleration, so FF. Make that applied force large enough that the naked eye sees that it's bigger. A football is moving upwards towards its peak after having been booted by the punter. Neglect air resistance. Diagram the forces acting upon the football as it rises upward towards its peak. Okay, well, football's played on Earth. Good. Anything else? Like that, Bailey? Objects in motion stay in motion. So, objects in motion stay in motion. You don't need forces to keep objects moving. Neglect air resistance. There is nothing slowing it down. Does the picture show, Josh, do these three-body diagrams show the direction that objects are moving? Not really. We don't care that it's moving upwards like this. We just care about the forces. That's the hardest one there is. And it, after having been moved. Yeah. No, good question. Always, always that question causes problems, and that's the one you had to be listening to the hardest. Number 11, car is coasting to the right and slowing down. Diagram the force acting upon the car. Okay, we got on earth, weight force. Alex, we got a normal force here? You. Yep. Convince me, you know.
Yes.
Okay, it's coasting to the right and slowing down. Alex, what's causing it to slow down? What force? Which way do I draw friction? It does in this case because it's coasting to the right and slowing down, so the friction should be right? Friction should be left. Is this going to slow down? Yes, it's got a net force. There is no applied force, unless you want to argue with me that even when your foot is off the gas, that the engine still applies a little bit of force to the car. Bam. Fair enough.